Welcome back, student. Now today we'll start in the next chapter, actually next module, that is basically compressible fluid flow. Okay, and the next chapter, that is compressible fluid flow. Now, as we know that the chapter name is compressible fluid flow, so first that will be question in your mind, that what is fluid. Now fluid is basically defined as a substance which continuously deforms under the action of shearing forces. Okay, it is basically defined as a substance which continuously deforms under the action of shearing forces. Now, liquid and gas both are actually fluid. Fluid in doesn't mean that only liquid is fluid. No, liquid and gas both are fluid, but depending on the various conditions, now fluid is generally in two types: incompressible and compressible fluid. Okay, now from that point of view, we can consider that incompressible fluid, that means its density doesn't change. Incompressible fluid means that is density doesn't change with uh, or something density or specific volume. You can say the specific volume also doesn't change with change in pressure or temperatures. But in case of uh, compressible fluid flow, the density change with a change in pressure or temperature or velocity. Okay, so that is called compressible fluid flow. That means the density is change. If you change pressure, temperature, then the density also, specific volume also change. Okay, then it is called the compressible fluid flow. Now, incompressible fluid flow is such type of fluid flow in which density doesn't change. If you change your pressure, temperature conditions, density doesn't change, or some changes maybe occurs. Okay, so that is called incompressible fluid flow. Now, one more example, that basically incompressible fluid flow are liquids are basically incompressible fluid flow, liquid. Okay, and gases are generally compressible fluid. Okay, this is a basic difference of the, or you can say this is the basic introduction part of your new chapter, that is compressible fluid flow. Now first thing is that what is fluid. Fluid is basically a substance which continuously deforms under the action of shearing forces. Okay, now liquid and gas are both are fluid, and fluid can be two types depending on its density, depending on the density, depending on the density changes. One is incompressible flow, and another one is compressible fluid flow. Incompressible fluid flow is such type of flow in which the density doesn't change. Okay, incompressible fluid flow is such type of fluid flow in which density doesn't change with a change in pressure, and compressible fluid flow is such type of flow where density change with change in pressure or temperature or velocity. Okay, and in the chapter compressible fluid flow, we generally basic principle which can be used in compressible fluid flow chapter, that is basically conservation of mass, that is sometimes also called continuity equations, which already I think you already gone through this, that what is continuity equation, that is basically discharge Q is equal to A1 V1, you can say Q is equal to rho 1 A1 V1 is equal to rho 2 A2 V2. Okay, Newton's second law of motions, or you can say momentum principle, conservation of energy, which is basically already gone through the syllabus in your first law thermodynamics basically, and second law thermodynamics, and equation of state. So these are the following principle can be followed in your compressible fluid flow chapter. Now this was the basically introduction part. Now the next topic in this chapter, that is velocity of pressure pulse in fluid. Okay, now as you see in your picture that so this is a piston cylinder assembly. Okay, this is a piston cylinder assembly, and now we can consider a so basically it's a totally filled up of fluid. So this is a piston, this is a cylinder assembly, and it is basically the pressure wave that generated by means of when piston travel from this direction to this direction, so from left to right, so there will be pressure will be generated, okay, and this pressure will be from a pressure wave front. So this is wave front that moves with velocity c here, okay. Now, so these are the things that happens in your piston cylinder assembly. Now you just consider that a infinite seminal pressure wave initiated by a slight movement of a piston to the right. So if you just initiated by slight or disturb, okay, if you disturb the fluid in a piston cylinder assembly, then the pressure wave are created, okay, in which the pressure wave front, the velocity term is c. Velocity term is c. It is sometimes also called velocity of sound. This c is basically called velocity of sound, or sonic velocity, or acoustic velocity, okay. Now, and the fluid near the piston, the fluid is basically here, that near the piston are basically, when you disturb, they slightly increase pressure in these sections rather than these sections, okay. The pressure increases in this section very much high compared to this section, so there will be some pressure wave generated in these sections. And when you disturb some amount of when you disturb the some amount of distance, when the piston when travel from this directions from left to right, and it travel x direction, then and total when the pressure wave front generate to the distance from the piston to L, okay, then the distance covered, so distance covers, it is basically covered in dt time. Now total distance covered in dt time for piston, that is x. If you disturb the piston in dt time, small interval of times at this dt, if piston travel from x direction, then the pressure wave front will be created, okay. If the pressure wave front is created, and the distance between the piston to pressure wave front, that is L, and that is x, okay. Now, so what are the distance covered in dt time for piston? That is x. So x is equal to, you know that v is equal to dx by dt. That means speed is equal to dx by dt. So x is equal to v into dt, okay, because piston travels with velocity v, right? So x is equal to v dt. Similarly, for pressure wave, that piston travel, the pressure wave generated, the distance is L. Similarly, the velocity is c. So the pressure wave as like L is equal to c into dt, because of, as you know, that dv is equal to dx by dt, right? Or you can say v is equal to dx by dt. So x is equal to v dt, right? So x is equal to v dt. From that concept also you can write down L is equal to c dt. Similarly, now the distance table. Now, so before compression, the parameters before compression, when you compress the fluid in the piston cylinder assembly, when the piston travels from the, so this is the ending position of the piston travel from this direction, the compression process takes place. When the compression process takes place, the before compression and after compression, so what are the thermodynamic property or changes that you can observe? Now before compression, we are assumed that the pressure was P here and the density was rho, okay. Now after compressions, the pressure will be increases, so that will be P plus dP in the time of dt, and density will be increase, that is rho plus d rho, okay. Now as you know that from the continuity equation, as you know that the before compression mass is equal to after compression mass, okay. So from the continuity equation, from the continuity equation, the before compression mass for length L. So before compression the distance was L. After compression X amount of distance piston travel. So the effective distance was L minus X. So the before compression mass for length L is equal to rho into A into L, rho into A into L, right? So because of A is the area, L is the length, rho is the density. So rho into V, actually the, if you get mass, so rho into V is your mass, so rho is your density. A is cross-sectional area of the piston cylinder assembly. L is the length, right? Now, previously you write that L is equal to CDT. Just write down here L in terms of CDT here, CDT, right? L is equal to CDT. L is equal to CDT. And after compressions the pressure increase as well as density also increase. That means pressure transform from P to P plus dP, and density changed from rho to rho plus d rho, right? So after compression mass for length L minus X, so after compression, when you compress the distance, the distance covered, that is minus L minus X, the effective distance. The piston travels this directions, this distance. So effective for length L minus X. Now for length L minus X after compression, that will be rho plus d rho, not actually P, this is rho plus d rho, because of, you know that the mass is rho into A into L. Now rho here after compression, rho plus d rho into A, cross section will be constant. Now length is here L minus X. Now you know that in the next line, you know that L is equal to CDT is the previous expression. So L is equal to CDT, right? And X is equal to VDT. So write down here L is equal to CDT and X is equal to VDT, right? From that concept. Now you just common here dt term. So C minus B into dt. So from the conservation of mass in the previous class, so in the conservation of mass, you know that the before compression the mass is equal to after compressions the mass. So total mass before compression is equal to after compressions. So that will be rho into A into C into dt is equal to rho plus d rho into A into C minus V into dt, right? So this one is equal to this equation. So this one is equal to this one. After all, you can see that A and dt will be rid off. Okay, A and dt, A dt rid off. So ultimately the equation becomes CD. Okay, now CD rho is equal to rho V. So CD rho is equal to rho V plus VD rho. So as because of here VDP becomes 0, VDP becomes 0. Okay, and the VDB or VD rho is equal to 0 because of the density change is very small. Okay, very small. So that's why this term is negligible. So ultimately the expression is CDP is equal to rho V, right? So this is the expressions. And now if you just apply pressure and force analysis, what is the amount of force before before compression, and what are the amount of pressure force after compression? Okay, now before compressions the pressure force is P into A, right? You know that. And after compression the pressure force will be increased. That means P plus dP, the pressure will be increased from P to P plus dP into A. Now as you know from that F is equal to M into A, right? F is equal to M into A. So total force that is basically P plus dP. So P plus dP, actual total pressure force created, that is basically in two directions. So P plus dP into A minus of PA is equal to M into A. Now M is equal to rho into A into L into A is your accelerations. That means dB by dt. dp by dt means change of velocity divided by change in time. Change of velocity is v minus initial velocity, that is 0, divided by dt. Got it my point? So f is equal to f sum is equal to ma. So after that, if you just calculate, then this will be cancelled out. Okay, here pa and minus p will be cancelled, so ultimately a dp, and in here rho into a into c into v, because L is equal to CDT. Write down here L is equal to CDT. So dt will be cancelled. So ultimately rho A C V, and here it is ADP. Now AA cancel. Ultimately dP is equal to rho CV. Right. From that equations, so V is equal to. So from that equations, so V equals to, or you can write down also C equals to, from this equation C is equal to dP by rho V, right? dP by, very important equation. So dP by rho V. Okay, dP is equal to rho V. Now here C dP is equal to rho V. Here C is equal to dP by rho V. Now you just write down, so the here in terms of V, or you can write down also from that equation V is equal to dP by rho C. V is equal to dP by rho C. So these two will be equal. So CdP is equal to rho into V. In terms of V, you can write down this one. In terms of V is equal to dP by rho C. Write down here dP by rho C. So ultimately CdP is equal to rho into dP by rho C. Okay, dP by rho C. Now C will be cancelled. Ultimately the expression of C square is equal to dP by d rho. Okay, dP by d rho. So C is equal to under root of dP by d rho. This C actually, velocity of sound, it is sometimes also called sonic velocity, or it is sometimes also called acoustic velocity also. Actually, no fluid is truly incompressible. There is no fluid is truly incompressible, although liquids show the little change in density. And the velocity of sound liquids in of the order of 1650 meter per second. Okay. So this was basically what are the velocity, pressure, pulse in a fluid. So ultimately the main expression was that C is equal to under root of, final expression was C is equal to under root of dP by d rho, where C is your velocity of sound, or sonic velocity, or acoustic velocity. Okay. Okay, thank you very much for listening me and watching me. Goodbye.